So it's a pleasure to be here. And let me thank Tridib, Sakuntala, Kavita for organizing this excellent gathering and also extending an invitation to me to participate. I'll be talking about this oscillating states in periodically driven Langevin systems. So in fact, this is the work done in, this is the work done with my student Shakul Avasti, and the details of this work can be found in these two references. I think before I start, probably I should mention that Langevin systems as well as periodic driving is something which was introduced to me by Mustansir. And I've also bothered Deepak with a huge number of discussions and so on when I was there in TIFR and occasionally whenever I met him. And I would like to thank them for that. Okay, so let me give a rough outline of the talk. So I'll give a very quick, a general motivation as to why one would like to study periodically driven thermodynamic or stochastic systems. Then I will give some details about the specific system that we have studied. In fact, more precisely, a driven underdamped Brownian particle in any potential, or rather any force acting on the Brownian particle. And so this is what I will describe. And so what we are interested in is what are the probability distributions at large time. Okay. So the take-home message, yeah, well, if you want to take home, is that there is an underlying symmetry in this particular problem, which is SL2 symmetry, and this symmetry can be exploited to exactly deal with the periodic drive and to any order in enharmonicity. Enharmonicity is this enharmonicity in this potential. Okay, so more precisely, what we have asked is what are the conditions under which these oscillating states exist, and I will mention what we mean by this oscillating state. And we also asked this question: if you can these oscillating states survive even against these enharmonic perturbations? Okay, so the rough motivation, of course, is periodically driven systems abound in nature. They're everywhere, from living systems to Earth's atmosphere. So my own motivation is that these driven systems, these driven macroscopic systems, actually can be stable. And when you drive them, if you have to imagine, you imagine a box of gas which is shaken periodically or stirred periodically, and wait long enough time, and at large times, probably these systems will exhibit will be in a state where the observables are periodic in time. Okay, and this is so basically there's some kind of a non-equilibrium state. It's of course different from definitely equilibrium or even steady state. And it is some state where the distribution is periodic, and this is what I refer to as oscillating state. So one of the motivations which for addressing this particular studying these systems is whether these oscillating states exist. And I also suspect that when you switch off the driving, then we expect the macroscopic. We know that the macroscopic systems has some kind of thermodynamics. And basically it is possible that even when you switch on this drive, this periodic drive, that there might be some thermodynamics which exists, and it would be interesting to know what this structure of this thermodynamics is. Okay, and there are of course other reasons as why study on these periodically driven systems is interesting. I believe that they are experimentally easy to access in the sense that you basically have to periodically drive these control parameters, and I also suspect that theoretically probably to say what are the properties of these oscillating states might be challenging. Okay, in the sense that it probably this is a question which probably may not be cannot be answered by our perturbative by our understanding of steady states or other thermodynamic states, other non-equilibrium states and so on. Okay, so let me Okay, so let me go to the specifics of this problem. So when we disturb, so what exactly is the dynamics? I mean, when we disturb a macroscopic system, these are known to be describable by Langevin within Langevin framework. So presumably, even periodically driven systems can be described by some continuous Markov process, essentially a Langevin dynamics or Fokker-Planck equation, equivalently Fokker-Planck equation. With some additional set of relevant variables, apart from the standard equilibrium variables, presumably there are other variables. And if you include this entire set, presumably there is a Markov process for this entire extended set. And so that basically that is nothing but the Fokker-Planck equation. And the parameters of this particular Fokker-Planck equations can be, some of them can be, some or all of them can be periodic in time. And so basically that is our dynamics. Hence, we have chosen this prototypical example of driven underdamped Brownian particle in any of your favorite potential. So the question that we ask is, do oscillating states exist? So what do we mean by that? Basically look at the probability distribution of this particular, solve this Fokker-Planck equation, and carefully take a large time limit. And if this particular probability distribution, which could be, if this particular probability distribution is normalizable, T periodic and independent of initial conditions, then we say that this oscillating states, they exist. Okay, so let me be a bit more quantitative. So or restate the problem. So basically, we consider the Fokker-Planck equation in this x and v variable, position and velocity variable, and this is the Fokker-Planck equation. And the parameters of this particular problem are the viscous drive here, this gamma, and the noise strength T. So these parameters. So these parameters are these parameters are time dependent. Apart from that, you could choose any force that you want. You can choose any force that you want. Basically, the harmonic as well as anharmonic forces. Usually, the anharmonic forces are functions of x variable alone, but the formalism that we have to handle this distribution, to exploit this symmetry and find this solution exactly. This is for that it doesn't matter even if you consider velocity dependent potentials. So the question that we would like to ask is the following: that you choose if you choose any viscous drive, noise strength D, and some mechanical drive, which is characterized by the harmonic potential strength as well as the harmonic strength, and the other the anharmonic parameters, make them time dependent. Then what is its large time distribution? Does it exist? And under what conditions this distribution exists? And that's a question that we ask. And so the way we go about solving is actually instead of looking at the distribution, we could write down the equations for all the moments and then find out what these moments are, what the solutions for these moments are. So the moments satisfy, of course, some differential equations. So we organize these moments as according to as some vectors, and basically which is denoted by this particular XL. So which is an L plus 1 dimensional vector, and these vectors these vectors, the components of vectors are nothing but the L moments. So for instance, x2 denotes a 3 vector with the components x square, xv, and v square. Okay. So if you write down the dynamical equation for these vectors, basically it has some homogeneous ordinary differential equation of this L plus 1 variables, and it has inhomogeneous terms which basically depend on lower moments. Okay. So the idea is so it turns out that the structure of these particular differential equation is the following. This particular matrix AL which we have here, it essentially consists of 3 matrices. It can be written as a sum of 3 matrices with these coefficient gamma and k. And these matrices, these particular matrices, turns out they actually satisfy this SL2 algebra. Okay, so that is an interesting fact. And apart from that, it turns out that these matrices are also irreducible representations of SL2. They are the generators of the irreducible representation of this the generators of the SL2 algebra. Okay, so then we exploit this particular theorem from representation theory.
You have 2 more minutes to finish.
Yeah. Okay. So we exploit this particular theorem from representation theory, which says that L plus 1 irreducible representation can actually be is nothing but a symmetrized tensor product of fundamental representation. So essentially, the summary of this particular exploiting this theorem essentially means that the solutions, this particular equation has L plus 1 solutions. I mean, there's an L plus 1 component first order differential equation, first order with L plus 1 variables. It has L plus 1 solutions, and these L plus 1 solutions can be obtained from actually the fundamental representation, namely actually the equations for the first moments. In fact, if the equations of first moments is it's a 2 component vector. And these solutions, let's call them as x1 and x2, x1 solution 1 and 2. And the solutions, this particular L plus 1 moment solutions can actually be gotten by taking the tensor products of these objects, R of this first solution, L minus R of the second solution, where R can be, 0 to L, and then basically symmetrize these. So in other words, that's how we actually find the solutions, and we found that in the harmonic case actually turns out to be a Gaussian distribution, which is not unexpected. This particular equation can also be thought of as a second order differential equation. There are 2 variables here, so it can be thought of as a second order differential equation of some 1 variable, some Hill equation. And in fact, this particular equation has an interpretation of a block, particle quantum particle in periodic potential, essentially an eigenvalue problem interpretation. So if you look at this equation, so we know this block equation, as you change the energy eigenvalues, not all, there are gaps which come in. The solution exists only for certain values, and it is exactly this condition, the existence of oscillating state condition turns out to be the statement whether these solutions, they don't blow up too fast. Okay, so that is a condition for the existence of this oscillating state. For example, if you change one of the parameters, some parameters, for example, as you change, sometimes you are in unstable. You don't have the oscillating state doesn't exist, and in some regions it actually exists. Okay, so that was our. So basically, we have, so this, to summarize, we have this exist, and we managed to find out under what condition these oscillating states exist. We could find out this distribution by solving a second order differential equation instead of third order differential equation. We can actually, it turns out that even if you have a potential which is, which is a harmonic potential, which inverted harmonic potential occasionally, if you invert it also at times, still the oscillating state can exist. The temperature of the bath is not the same as the temperature of the system, and in fact, this particular variable x and v variables, they cannot be decoupled when there's a drive. In general, both these variables have to be included to understand the system, and so on. So not only that, we did ask the question, if you include perturbations, whether these perturbations can destroy this oscillating state. And it turns out that the distribution in presence of these enharmonic terms, we can organize. You can organize in this homogeneous sectors, where each of these vectors, again, turns out you can write down the dynamical equations for these vectors. And it turns out, again, this particular symmetry can be exploited to solve this distribution. In other words, we can actually find the distribution to any order for any kinds of polynomial perturbations, and by exploiting this particular symmetry. Okay. So it turns out that surprisingly, so this particular, again, the structure of this equation turns out it depends on these two variables, gamma p and kp, which are which are not only functions of gamma and k, but
Professor, can you please
yes,
finish?
I'll just take a half a minute. So so they also depend on this distribution, this harmonic distribution. And they are reasonably different from this gamma and k. Yet, what we so basically we did ask this question: can enharmonic perturbations destroy these oscillating states? And it turns out that so it turns out the answer we found was actually no. In fact, it turns out that the condition for boundedness of these particular coefficients turns out it is exactly the same as the condition for existence of oscillating states in the harmonic case. So I think with that I think I'll stop here. Yeah, thanks.
Thank you. Okay, are there any questions? We can take some quick questions. Okay, so if not, then let's.
I want to make a comment.
Yeah.
So, Sreedhar, it looks like there might be a more general proof for the statement that there will be oscillating states which doesn't require exact solution.
Which
That
you mean?
there might be a way to show that the periodic solution exists without finding it exactly, explicitly.
Yes, probably, yes. Yeah. No, I think, Deepak, you can formally one can make a you look at the formally one can write a Fokker-Planck equation, some operator, and then you can construct basically you can look at this what you call this the evolution operator between 0 and 1 period, and if the eigenvalues of this, based on the eigenvalues of this, you can essentially say whether or not the solution exists.
Okay, thank you.
Thank you, Professor, for this wonderful talk. Okay, so this concludes our session. And I would like to thank all the speakers for their interesting talks and everyone present in this session for their kind cooperation and making it a nice experience for me.